Dubai's glass towers look perfectly still. They are not. Under the desert sun, the metal frames expand. The glass moves differently. Between them is a thin, flexible layer that has to absorb the difference. It does this today. It has to do it again tomorrow. Then through another summer. And another. But what happens if that movement is no longer absorbed exactly where engineers intended? The force does not simply disappear. It moves into the facade. That is the moment when movement too small to see can become an engineering problem large enough to demand inspection, repair, or replacement. And on a tower, covered with thousands of heavy glass panels, that makes a tiny line of material far more important than it looks. From the pavement, none of this is visible. You see reflections, clean lines, and a surface that looks almost sealed from the world outside. But behind that polished appearance is a network of interfaces constantly making tiny adjustments. Some movement is measured in amounts too small for a tourist to notice. That does not make it irrelevant. On a facade, small movement is exactly what joints are designed to manage. The engineering challenge is not to stop physics. It is to give physics somewhere safe to go. And once you understand that, the skyline stops looking like a collection of solid objects. It starts looking like a collection of controlled movements. That is the mystery at the center of this story. This is the hidden struggle inside Dubai's skyline. It does not begin with a dramatic collapse. It begins with heat. It begins with two materials trying to move by different amounts. And it begins again the next morning. Dubai's own building guidance has long used an outdoor dry bulb design temperature of 46 degrees Celsius for cooling calculations. It also recognizes a large daily outdoor temperature range. That does not mean every facade reaches the same temperature or that heat alone will make a tower fail. It means extreme thermal conditions are not an abstract idea here. They are part of the environment engineers are expected to design around. So the real story is not that Dubai forgot about the desert. The real story is that the desert never stops asking the buildings to respond. Imagine a glass panel locked into a rigid metal frame with no ability to move. As the sun heats the exterior, the frame changes dimension. The glass changes too, but not in exactly the same way. If every part were forced to behave as one perfectly rigid block, stress would have nowhere useful to go. That is why modern facade systems include components that can accommodate movement. Structural silicone, weather seals, gaskets, anchors, and joints can all play different roles depending on the facade design. Some help keep air and water out. Some help transfer loads. Some allow controlled deformation. Some do several jobs at once. The important idea is simple. A skyscraper survives movement by managing it. That changes the way you should look at a glass tower. The most interesting point may not be the middle of a giant pane. It may be the narrow interface where glass meets metal. That is where materials with different behavior are asked to cooperate. Research on structural glazing treats movement, strain, temperature, humidity, and ultraviolet exposure as real durability questions. Researchers do not test these systems because failure is guaranteed. They test them because long-term performance depends on how materials behave under combinations of weather and mechanical demand. And this is where the story becomes less comfortable. Dubai does not ask these joints to work once. A facade heats. It cools. It heats again. It faces sun, humidity, wind, cleaning, and ordinary aging. The tower can look identical from the street, while its outer skin is constantly accommodating small changes. One hot afternoon is not the real enemy. Repetition is. To understand the scale, look at the most famous tower in Dubai. Burj Khalifa's official description says its exterior cladding contains close to 26,000 glass panels set within aluminum frames. Each panel weighs about 362 kilograms. Those numbers are not evidence that the tower is unsafe. They show how enormous the facade engineering problem becomes when a single building is wrapped in thousands of separate pieces. One panel can expand. One frame can move. One joint can deform. Now multiply that logic across an exterior stretching hundreds of meters into the sky. The official Burj Khalifa description also notes that the glass uses a silver coating intended to limit solar heat gain and cope with Dubai's extreme summer environment. That detail matters. It proves the heat problem was never hidden from the designers. The facade was created with the climate in mind. But that does not end the story. It actually makes the next question more important. Why does a building need so many layers of defense in the first place? Because glass towers are not passive objects. They are systems. The coating manages solar gain. The framing supports and positions panels. Joints accommodate movement. Seals help control air and moisture. Anchors and connections transfer forces back toward the building. Every layer has a job. And if a layer loses performance, the tower does not instantly collapse. That would be a dramatic claim unsupported by the evidence. The more realistic concern is local. A joint may no longer seal as intended. Movement may become more restrained. Water may reach places it was not supposed to reach. A connection may be asked to tolerate a condition that was supposed to be absorbed somewhere else. The danger grows through a chain, not through one cinematic moment. But scale is still not the most important part. The most important part is that tomorrow, the system has to do its job again. At sunrise, a glass facade begins another cycle. Different parts of the building receive sunlight at different angles. Some surfaces warm earlier. Some stay shaded. Later, the geometry changes again. Then evening arrives and temperatures move in the other direction. The result is not one simple expansion of an entire skyscraper like a balloon. It is a complicated pattern of local movement across materials, orientations, connections, and temperatures. That distinction matters because glass can also experience thermal stress when temperature differences develop across a pane. Engineers consider these effects when selecting glass, coatings, framing, shading conditions, and edge details. Again, the existence of thermal stress does not mean glass is about to break. It means temperature is a real load case that has to be controlled. The same logic applies to seals and joints. A component that stretches and returns once may perform perfectly. The meaningful question is how it behaves after repeated exposure to movement and weather. NIST research on building sealants has examined outdoor weathering together with static and dynamic strain. Other durability studies expose structural glazing systems to combinations of ultraviolet radiation, temperature, humidity, and mechanical loading. That combination tells us something important. Engineers do not separate the weather from the movement because the facade does not experience them separately. Dubai makes that interaction easy to understand. The sun heats the envelope. The interior is cooled. Humidity can be high. Glass, aluminum, sealants, and concrete each respond according to their own properties. Then the entire process repeats. There is no final summer after which the building is finished with heat. For as long as the tower remains in service, the envelope must keep managing the environment around it. And that turns a temperature problem into a time problem. This is where many dramatic stories about Dubai go wrong. They treat heat as if it were a hammer. One brutal afternoon arrives. Something cracks. The tower suddenly becomes unsafe. Real facade engineering is usually less cinematic and more interesting. A good sealant is supposed to be flexible. A well-designed joint is supposed to move. A coating is supposed to reduce solar gain. A frame is supposed to accommodate the geometry and loads assigned to it. The danger is not that these defenses exist. The danger is assuming that because they worked on day one, they will need no attention years later. Materials age. Surfaces weather. Buildings are cleaned. Components are inspected. Some items are repaired or replaced. The performance of an envelope is something that has to be preserved, not simply installed once and forgotten. This is why durability research matters. A recent study of structural silicone glazing examined how temperature, humidity, stress, and ultraviolet radiation influence long-term performance. NIST has also spent years studying the service life of building joint sealants under environmental exposure. The conclusion for a viewer does not need to be technical. The solution has to survive the same environment it is protecting the building from. That creates the central paradox of Dubai's glass skyline. The hotter and harsher the exterior becomes, the more important controlled movement becomes. But the components that control that movement are physical materials with their own service history. So the question changes. Can Dubai build towers that survive extreme heat? Clearly, yes. The skyline already exists. The harder question is whether every critical part of every aging facade continues to perform as intended year after year. That is not a prediction of collapse. It is a maintenance challenge. And maintenance is where the glamour disappears. There is a moment in this story when everything should feel reassuring. Engineers know that materials expand. They know glass facades move. They know seals need flexibility. They know the Gulf is hot. They know ultraviolet exposure exists. They know buildings age. Dubai's codes and building guidance reflect a climate where cooling loads and envelope performance matter. Burj Khalifa itself uses double-layer glazing, aluminum frames, and solar control coating. Modern facade systems are designed around movement, wind, water, thermal performance, and maintenance. So perhaps the problem is solved. For a moment, that is exactly how it looks. Then one word changes the story. Time. The engineering solution is not a magic shield. It is a collection of components that must remain inside acceptable performance limits. That means inspection matters. Installation quality matters. Drainage matters. Seal condition matters. Replacement decisions matter. Access for maintenance matters. The building may be permanent in the imagination of a tourist. The facade is a working asset. And a working asset has a history. Every summer adds another season of exposure. Every cleaning cycle adds another interaction with the exterior. Every repair creates a new interface between old and new materials. Every year moves the building farther from the day it was completed. None of that means failure is inevitable. It means successful survival is active, not passive. Dubai's skyline stays impressive because somebody keeps managing the details people never photograph. Now imagine one local joint that is no longer accommodating movement as intended. Do not jump straight to a falling tower. Follow the engineering chain. First, the joint may lose part of its ability to seal or deform correctly. That can change how movement is distributed locally. If a weather seal is compromised, air or moisture may find a path through the envelope. If movement becomes restrained, nearby components can experience different stresses. If water reaches concealed areas, it can create additional maintenance problems. If a local connection is damaged or badly deteriorated, the facade may need repair before the problem grows. Each step is smaller than a skyscraper collapse. That is exactly why the chain is believable. Most building problems do not announce themselves with a movie scene. They begin as inspection findings. A crack, a failed seal, a leak, a loose component, an area that moves differently from the way it should. The danger comes when small findings are ignored, misunderstood, or allowed to combine. This is why maintenance systems exist. They are not evidence that a building is failing. They are part of what prevents manageable defects from becoming larger problems. But on a very tall building, local facade safety still carries serious stakes. Remember the Burj Khalifa panel we mentioned earlier. About 362 kilograms. Earlier, that number sounded like trivia. Now it explains why engineers care so much about the frames, seals, anchors, and inspection routines surrounding every panel. A facade component does not need to bring down the building to create a serious safety issue. The envelope itself is part of the safety system. That is the real meaning behind the phrase, pulling apart. Not a city ripping in half. Not towers suddenly collapsing in the sun. A constant contest between thermal movement and the systems designed to keep that movement controlled. There is another reason this matters in Dubai. The skyline is not only infrastructure. It is part of the product Dubai sells to the world. In 2025, Dubai welcomed 19.59 million international overnight visitors, according to the city's tourism authority. That was another record year. Visitors come for beaches, shopping, hotels, entertainment, and business. But the skyline is the visual promise connecting all of it. Burj Khalifa, the towers along Sheikh Zayed Road, downtown Dubai, and the glass canyons of the marina tell the same story. This place is engineered, polished, reliable, and futuristic. That makes maintenance more than a technical issue. It becomes a confidence issue. Earlier in 2026, regional travel disruptions hit Gulf tourism and weakened traveler confidence. Dubai was not dealing with a facade crisis. The events were unrelated, but they revealed something useful about the city's economic model. Perception matters quickly. A tourist does not need to understand curtain wall engineering. They only need to believe the destination works. That is why a visible facade problem on an iconic tower can matter beyond the repair bill. A closed entrance, a restricted area, scaffolding around a landmark, repeated stories about damaged cladding. Any of these can become part of the public image of a destination whose brand depends heavily on precision and spectacle. This does not mean heat is causing a tourism collapse. It means engineering reliability supports tourism confidence in ways most visitors never notice. Dubai sells the finished image. Maintenance protects the image. That relationship is easy to miss because tourism rarely appears in an engineering drawing. Yet a destination built around record-breaking architecture depends on people trusting that the spectacle is being managed. The visitor sees a finished surface. Behind it are inspections, access systems, cleaning crews, engineers, contractors, replacement schedules, and budgets. When all of that works, the experience feels effortless. That effortless feeling is part of the product. And in a city built around extraordinary architecture, the line between the two is very thin. Dubai's next skyscraper challenge may be different from the one that made the city famous. For decades, the question was how high the next building could rise, how quickly a new district could appear, how much glass could be placed against the desert sky. Now another question is becoming unavoidable. How do you keep an enormous existing skyline performing for decades? A new facade begins with new seals, new coatings, new connections, and a documented installation condition. An older facade has a service history. It has experienced heat, humidity, ultraviolet exposure, wind, cleaning, repairs, replacement parts. Thousands of ordinary daily temperature changes. That history does not automatically make an older tower dangerous. Many facade systems can perform for long periods when properly designed, installed, inspected, and maintained. But age changes the job. The goal is no longer simply to prove that the original design works. The goal is to confirm that the real building, after years in the real environment, still behaves close enough to that design. This is where inspections become more valuable than assumptions. A skyline can look unchanged from a helicopter while individual joints are being replaced. A tower can remain open while sections of facade are repaired. Maintenance can be extensive without becoming visible to the public. That invisibility is actually a sign of success. The best maintenance story is often the one tourists never hear. But invisibility also creates an illusion. Because we do not see the work, we imagine the tower needs none. Look at Dubai from a distance, and the city appears almost geological. Glass cliffs rise from flat desert. Their surfaces reflect the sky. Nothing seems to move. But now you know that stillness is manufactured. The facade is allowed to move so the building can remain visually still. Flexible materials deform so brittle materials do not have to absorb every change. Coatings reject part of the sun's energy. Frames, anchors, drains, seals, and joints divide a huge environmental problem into thousands of smaller engineering tasks. That is why the most dramatic conclusion would also be the least accurate. Dubai's extreme heat is not proven to be making its skyscrapers collapse. There is no evidence that the skyline is on the edge of a heat-driven structural failure. The more interesting truth is almost the opposite. The towers survive because engineers assume the environment will keep attacking the envelope and design systems to accommodate it. The vulnerability appears when we forget that those systems need care. Dubai did not make the desert disappear. It built an enormous machine that continuously negotiates with it. Every summer, the negotiation begins again. Every joint has to accommodate movement. Every seal has to keep doing its job. Every inspection has to separate cosmetic aging from something that needs repair. Every maintenance team has to catch small problems before they become larger ones. That is what makes the Skyline impressive. Not that it never moves. That it moves, ages, expands, contracts, gets repaired, and still manages to look perfectly still. The next time you see sunlight flashing across a Dubai tower, do not just look at the glass. Look at the thin lines between the panels. Those quiet interfaces are where the desert and the city meet, and they may be doing far more work than the Skyline lets you see. This video is an educational analysis of facade engineering, thermal movement, material durability, and maintenance in hot climates. It does not claim that Burj Khalifa or any specific Dubai skyscraper is currently unsafe, failing, or at risk of imminent collapse. Building performance depends on the design, materials, installation, inspection, maintenance, and operating history of each individual structure. The examples discussed here explain general engineering mechanisms and publicly documented design information, not a diagnosis of any specific building. If this changed the way you see Dubai's skyline, subscribe for more stories about the hidden engineering systems behind the world's most extreme cities. And tell me which Dubai landmark you want investigated next.